So thank you all for coming. Just to reintroduce myself, I'm Alexandra. I'm a new postdoc here, working with JF. So today I'll be telling you about the code equivalence problem. And I'm going to sit actually because my hand doesn't shake as much. So forgive me for that. Okay, so first I'm going to recall some of the concepts that Freeman told us about in his first seminar talk a few weeks ago now. So in particular, I'm going to recall that a linear code is defined by a generator matrix so over a finite field of size q. So it's a full rank k by n matrix. K is less than n, at most n. Okay, and it's generated in this way. I'm going to take all code words. They're made by multiplying a vector by the generator matrix, where the vector coefficients are over fq, right? So this is a linear code. So these are the codes I'll be talking about today. So the code equivalence problem asks for the following. Also, if you have any questions throughout the talk, feel free to interrupt me and I can address them. So this problem states the following. Given two linear codes, which are given by their description, the generator matrices, so G1 and G2, determine if they're equivalent. So I'm going to use the squiggly equals as a, shorthand for this. Okay, so also recall, I should have said before, but also recall that generator matrices are not unique. All right, so in particular, I know that the code generated by generator G is the same as that generated by SG for any invertible matrix S in the general linear group. Okay, so these are important for today. So I told you about the code equivalence problem, but what does it actually mean for them to be equivalent? This is what the variants of the code equivalence problem tell us. So I can ask whether two codes are equivalent up to permutation. So this gives us the PCE problem. So in particular, like if I'm given two codes, determine if there exists an invertible S and a permutation matrix P such that S times G1 times P is G2. Right, so here for these problems, I have to allow for these invertible matrices S because I want to capture the fact that the codes are equivalent, not that the matrices are equivalent, right? So this is why it exists throughout. And I can generalize this further. I can allow not just permutations, but sign permutations, let's say. So sign PC, which I'm going to abbreviate by SPC from now on. So this is the same thing, but now I'm allowing, matrices from SB. So I'm allowing plus minus one scalings, right? Okay. And then the last one, which we'll be focusing on today, there are more, but last one for us is linear CE. So LCE. And for this one, I'm generalizing further to monomial matrices, and I'll recall what these are in a minute. Okay. All right, so just to recap. So the set of monomial matrices over a finite field. This is all matrices that can be decomposed into a diagonal matrix multiplied by a permutation matrix. So D is some diagonal matrix where with non-zero field elements along the diagonal. And then P is a permutation matrix, right? So now I've gone from allowing plus minus 1 scalings to any non-zero scalings in the permutation matrix. Okay, so another way to write this is actually the semi-direct product of Sn and Dn, where Dn is the group of non-singular diagonal matrices. Okay, so just another way to phrase it for people who come from very different backgrounds, but the linear CE problem essentially is asking if I can find a linear isometry, right, that takes one code to the other. So I can generalize this even further and say, okay, I'm not only allowing linear isometries, right, linear isometries T that will take my first code to the next, but I can also allow field automorphisms, alpha, right, for this. So this, I'm not going to write the full thing here, but this version I believe is often called sesquilinear code equivalence, which we won't talk about today. It's just an interesting one. Okay. So let's see some examples before we move on. So let's say I'm restricting my field. I'm looking at the field with 5 elements. And take this generator matrix 2, 1, 0, and then 0, 0, 1. And then let's say I give you this other generator matrix 0, 2, 1, and then 2, 0, 0. How are these equivalent? So if you squint a little bit, you can see that this is just a shifting of the coordinates with one scaling. So for a permutation matrix, we have this. And then we're leaving the first generator vector alone and then scaling the second one to get this. So in particular for this example, G1 and G2, satisfy the PC condition. So all throughout, you'll hear me say like, this pair is in PCE or satisfies PCE. All of these mean the same thing. There's a little nuance, complexity theory-wise, but I won't go into that today. So, all right. Okay, so we can also allow plus minus 1 scalings. So let's say I do this. Then here I would get something like this for the generator. All right, so same structure, but a little less obvious to find. Okay, and now let's see, just for completeness, if I scale it by, let's say 2 and 3 in the field, I get something like this. Right, so right, these ones are in LCE now. Okay, any questions so far? Okay. Okay, so these sets, so actually let me clarify this. For a given finite field FQ, I'm just going to use this notation. I'm going to cut out the field whenever it's clear. So the permutation, the set of permutation matrices is a subset of the sign permutation matrices, subset of the monomial matrices, and in turn is a subset of the general linear group. Now these are all matrix groups that act on the set of linear codes in FQ to the n. Okay, right. So because of this, intuitively, this tells us that if I have a PCE instance, it automatically means it's SPCE and is also LCE, right? So this comes just from the matrix group structures. Okay. So, right, I showed you 3 different variants of the CE problem. Why do we care about these? So, one reason that they're increasingly important is that they're all used as the basis for some crypto systems that are recently proposed, including some NIST submissions just in the last few years. But not only the CE problems are used for this, it's part of like a class of problems of finding isomorphisms between objects, right? So let me write it this way. Let's see. So it's used as the basis of many recently proposed cryptographic schemes. Okay, including some NIST submissions. So, yeah. So because of this, like it's increasingly more important to understand how these types of problems relate to each other, how hard they are to solve, right? And how they can reduce to the relationship between them. So today, I'm only going to focus on reductions between isomorphism problems. And then next time, I'm going to show you the cryptographic applications based on these, with these as the basis, sorry. Okay. All right. So there are actually 2 kinds of reductions that we'll be focusing on today, and I'll define them for those who are not familiar. So the first that we'll see is the Turing reduction. So this means that I have a problem. I have 2 problems, A and B, all right? Problem A reduces to problem B if and only if problem A can be solved using an oracle solver for B. So what this means is if I know how to solve B, I can use that algorithm to solve problem A, right? And what I really care about is that this solving one problem with another can be done in polynomial time. So in polynomial time, and oftentimes you'll see this kind of reduction with the polynomial time being called a Cook reduction, but I just used Turing. Okay. And the second kind of reduction that we'll see is the Karp reduction, which is a bit stronger. in the following sense. I not only care about solving one problem with another, but I care more about transforming an instance of a problem into the other. So I'm essentially showing that both problems have the same structure. So let's see. It can be transformed into an instance of B in polynomial time. Okay, so what this means, transforming one into the other, is if I have a yes instance for A, right, so if whatever input I give to A satisfies the conditions needed, right, for it to be a yes, then it must also satisfy the yes conditions for B, the transformed problem, right? So if I take the input to A, transform it under this reduction, I have to get an input for B that will output a yes, right? And the same for no. So that's why I mean this is a much stronger kind of reduction. Does this make sense so far? Okay, all right. So what I'm going to show you today is a map of reductions between these CE variants and other isomorphism problems. The first one I'll show you is the search PCE to decision PCE. So, okay, let's look a little more carefully at the problems I defined. So all of these problems, the way they're phrased is given an input, decide if something exists, right, that satisfies this condition. So these are called decision problems because I output yes or no, right? But I can also ask for, I can tweak this a little bit and ask for the following. Like if I'm given two equivalent, let's see, two equivalent generators. So for PC, it's up to permutations. I want to actually find that pair of matrices that shows that they're equivalent, right? So I'm guaranteeing that these are equivalent now. So find S and P such that the condition holds. All right. All right. Yes. Mm-hmm.
Are you saying that you can decide whether something is equivalent without finding the equivalence?
No, it's the other way around. If I know how to decide whether two things are equivalent, I can actually find the pair of matrices that shows the equivalence. Right, so Giacomo can.
Yeah, so never happens in practice that you can decide, but you can, like, it's just a theoretical thing. These are different problems. Right, am I saying it?
Yes, yeah.
Right, so like deciding doesn't guarantee that you can actually find. Right. But yes.
Yeah. Okay, so on that note, this reduction was actually showed by JF and Giacomo a few years ago. So in particular, they show that there's a Turing reduction from search PC to decision PC. This means that any search PC instance can be solved with a polynomial number of calls to the oracle for decision PC. So I'll try and abbreviate this, but okay. All right, so I'll give you a high-level idea for how this reduction works because it actually ties into some of my work later on. Let's see. Okay. And if you want me to go back, just let me know. Okay, so here's the proof idea. So remember that if as the input to search PCE, I'm given two equivalent codes, right? So I'm given G1 and G2. Such that SG1 P G is equal to G2 for some S and P. Okay, and my goal is to find this S and P. So how do I do it? Their algorithm does this. It basically tests not all, but all possible permutation maps, and picks the one that works for every index. So it finds the permutation matrix given by this permutation map. So just a note, I'm using this notation to mean all the integers between 1 and n inclusive. Okay. So by iteratively testing whether this works, whether column J can be mapped to column IJ for every single index. So for a given J, we're going to do this. We're going to extend the given generator matrices in the following way. So if this is my G1, let me just show you G1. If this is G1, I'm going to copy its jth column m times. Where m is one more than the maximum number of times a column appears in G1, right? So I'm ensuring now that I have a column here that appears far more than anything else appears in G1, right? Okay, so I do this, and then, so this is my new matrix, G1 prime. And I do the same thing for G2 prime. But now I'm copying the ijth column. So I'm denoting the columns by hij here. Again, m times. And then I'm going to query these two new generator matrices to my oracle. So query G1 prime and G2 prime to the PCE oracle. So if it says yes, like yes, these are equivalent, then it means that this mapping worked for me, right? So I'm going to set it. I'm going to fix this mapping. Okay, otherwise, I'm going to try again with some new, image, ij prime, let's say, right? And I do this for every single jn, but I can't do this independently for each of the indices because different solutions to these like subproblems can not necessarily make a big solution that I need, right, to map this to this consistently. So what I do when I iterate, like for every single index, I keep building on this map. I keep adding copies of these m columns, right, for every single column that I have. Okay, so this is the general idea, right? Just this iterative search. Okay, so let me actually, so this is one piece of our map. Search PC to PCE. So we also know that LCE reduces to PCE. So this was shown by Sandrière and Simons. in 2013. So they actually show that there's a Karp reduction, so the stronger reduction from LCE to PCE. Okay, so here, also, when we say polynomial time, it has to be polynomial in the size of the input. We do care about exactly what. So for our case, n is going to be the block length of the codes, of the input codes. And then q is the field size, right? So same notation we've been seeing so far. Okay. So they do this just as an idea. They use this notion of a closure of a code. So if I have a code C, the closure C tilde is defined by multiplying every single code word by every single element of every single non-zero element in the field. Okay, every code word I have, and then okay. So they create this different set where each element has n times q minus 1 coordinates, right? So why do they do this? Basically, they notice that every single non-zero element in the field, it induces a permutation on the code words, right? So scalar multiplication basically is equivalent, in a sense, to permutation of coordinates. Okay, so this is the idea they use to tie together that the non-zero scaling in linear CE is basically the same as like permutation, as the permutation in PCE, right? So this idea was extended and used further to show that SPCE also reduces to PCE and LCE reduces to SPCE. Okay, so this one is by Dukas and Gibbons in 2023, and this is by Bennett and Nguyen, 2024. Okay, so both kind of use an extension of the closure idea. Okay, all right. So this is our map so far that we hear. Now I'm gonna add a little more to it. Okay. So we also know that the reverse reductions work. I can reduce PCE to SPCE and PCE to LCE, also using Karp polynomial time Karp reductions. Right. So this one is by Chiragchi, Shagrithaya, and then me just this year. So we actually use a very similar technique to the construction from Bias-Micheli to prove the search decision reduction here, right? So not the closure technique. So in particular, we show that there exists a polynomial time reduction, but polynomial in n and log q. So it's a little bit better. Okay, all right. So, okay, maybe just a side note, just to drive this home, but it's not actually obvious that this is true. So it's easier for us to say that a PCE instance is an SPC instance, right? Because the set of permutation matrices is a subset of the sign permutation matrices, right? But to reduce a problem to the other, using a Karp reduction, I have to transform it so that I not only have a yes instance mapping to a yes instance, but I have the no mapping to no. That last one is hard. It's like that, proving that last direction is not always the case. It's not always possible. So that's the tricky part for this. So I'll show you a little bit of how we managed to do this. So here's the proof idea. Also, these two reductions are actually very, very similar in how we prove it. The only difference really is that you allow non-zero scaling versus plus minus one scaling, but the construction that we use is almost identical, right? It's just the analysis that's different. So here's what we do. So if I'm given two generator matrices, G1, G2, I'm going to transform them into two matrices, G1, G2 hat, okay, which are a little bit bigger, so K prime by N prime, in the following way. So I'm going to take my G1 generator. Then I'm going to copy the first column, m times, and every single one of its column also m times, right? Just one after the other. So right here I get an n by m number of rows. And then I'm going to append a lot of zero columns. In particular, I want n times m plus 1 of them, right? So m is actually the same thing we saw before. It's 1 plus the maximum number of times a column appears in the given matrix G1. So here I'm ensuring that I'm adding G1 far more times than it appears in G1. The same thing for all these other columns. And then the most common column that appears in this whole thing is the all zeros column, right? Little bit of nuance, I can assume without loss of generality that the all zeros column does not appear in G1 because I can just take G1 and G2 to be full rank. If they're not, you can reduce it further to the case where they are. So that's a key point here. And then aside from appending all these copies, I'm going to append this last row where it's ones in the first block, right? And then zeros in the second block, and then ones all in the third block, right? And you'll see why we do this in a bit. But this gives us a matrix, which is k by 1 times, let's see, 2nm plus n plus 1. Yeah. So this is our k prime and n prime. Okay, so m is at most n, So this construction is in polynomial time, right? And we're not actually using, we're not iterating through the field elements. So for us, it's enough to just represent the field elements using log q. So that's where the polynomial in n and polynomial log q come from, right? That makes sense? Okay. So for our purposes, I'm going to label this block matrix as one by 1. This is block 2, and then this is block 3. Okay. So here's the easy direction, where I want to show that I can recover, oops, sorry. Where for any SMP, right, such that the PC condition holds, I can actually construct two matrices, S prime and M prime, that satisfy the LCE condition. Let me label these differently. Okay, right, so this is the case where I'm mapping a yes instance of PCE to a yes instance of LCE. So how do I do this? I can just take the whatever S I have. So I don't actually know what these look like necessarily. I'm just saying whatever S is, take any S, this is how you would make an S hat, right? So you just put whatever S and P that exist into this algorithm, and this would spit it out. But I don't know what these actually look like on the inside. Okay, so I'm making this slightly larger matrix, just adding a 1 here and zeros everywhere else, right? So this one is still a permutation matrix. And then I'm building M hat in this following way. Okay. I'm taking P, whatever it is, and then I know that P induces a permutation map, right? So wherever it sends the first column here, I'm going to just say P, this block, the permutation map defined by this, is going to send these columns also off to the offset location for the other columns, right? So in particular, if 1 is being sent to 2 in G2, I'm going to send everything here to wherever the second columns are sent in block 2, right? So this is just index matching really for this part. And then this is the identity, right? I'm just sending everything here in this third block to the third block. Okay. So this is a monomial matrix, right? Just by definition. Okay, now for the hard direction. Now we want to recover these matrices from whatever these things may look like, right? So here's how we do this. Okay, I'll hand wave a little bit, but basically the structure here, we build this in a very particular way that basically ensures that everything in the first block in G1 is being mapped to the first block in G2, right? Second block is mapped to the second block in G2, third to the third. So basically there's no columns that are being permuted between these three main block matrices, right? So let's see. let me actually step back a little. So our goal here is to recover S and P. Okay. So the structure the first block of G1 hat is mapped to first of G2 hat, second to the second, then third to the third. Okay, so let's take this apart a little bit. This is ensured by the column frequency, right? We copied these columns in such a way that they have a very specific frequency distribution, right? And in addition to that, we also ensured that we have these ones here, zeros here, and ones here. This means that no column here in a block exists anywhere else. So even though I copied this column from G1, this entire column of the new matrix does not exist anywhere else. Right? So this forces any kind of pair SM to respect these boundaries. Right? So in particular, with quite a bit of analysis, we can show that S must have this structure, S hat must have this structure. It's some invertible matrix S with a non-zero element here and zeros everywhere else, right? So then the monomial matrix also has a very similar structure. Because it respects these boundaries, it looks like this. So same as before, as here. But we don't know that's the identity, right? So we only know that these are smaller monomial matrices. Okay, and then what we do is we take this is our S, and then this is exactly our P. Okay, so why is this monomial matrix necessarily a permutation matrix? This is ensured by this last row here. If you had any other non-zero scaling besides 1, this last row would not have been mapped to all ones in the second matrix, right? So that's the gist of it. Yeah. Any questions? It's a bit hand-wavy, but. Okay. All right. Okay, so this is our map that we have for CE variance. Okay. All right. But there are other isomorphism problems that we care about. So I'll give you 2 today. This one is called graph isomorphism. It's a very well-known problem. So I'm going to abbreviate it by GI. So this says, if I'm given 2 graphs, let's see, over the same set of vertices, determine whether there exists a permutation of the vertices that gives a bijection on the edges. Okay. So here's an example of what this could look like. Let's say I have the pentagon graph. With vertices 1, 2, 3, 4, and 5. So this is actually isomorphic to the star graph. with these vertices, and you can see it by just mapping the edges. So 1, 2 is, whoops, map to this one, 2, 3, let's map to this one, 3, 4 is here, 4, 5 is here, and then 5, 1 is here, right? So this is one example of two graphs that are isomorphic to each other under this mapping, given by the colors. Okay, so another isomorphism problem is the lattice isomorphism problem. So this is abbreviated by LIP. So this asks for the following. Let's say I'm given two lattice basis matrices, B1 and B2, and I'll define what these mean in a minute. But these are n by n real matrices. Determine whether there exists an orthogonal transformation given by this matrix O. And a matrix U, invertible matrix U, over the integers such that I have O times B1 times U is B2. So very similar to what we saw for the CE problems, right? Okay, just an aside. This is what a lattice is. So if I'm given a basis matrix, the lattice generated by the basis matrix is the set of all integer linear combinations of the basis vectors, right? So we can denote it by this. So this is actually a discrete additive subgroup of Euclidean space. Okay, here's an example, a very simple one. But let's say I take the integer lattice in 2 dimensions, like this, right? So this is generated by the basis vectors 1, 0 and 0, 1. And this is actually isomorphic to a rotation and scaling, any rotation and scaling, but for example, this one. So here's one way. There are other basis vectors. You could do this one and this one, for example, but yeah. So these two are isomorphic. All right, so for these problems, we can get a much more interesting picture. So we actually know that these variants, well, all variants of CE reduce to LIP. And the graph isomorphism problem reduces to all variants of CE. So these were also shown by Bennett and Wynn. Okay, so this is the map, the landscape that we have for all these isomorphism problems, right? Hopefully I'm not missing any. If you complete the triangles, yeah. This is transitive. Okay. So what this tells us, just as a general idea, which will be useful for next time, is that since GI reduces to the variance of code equivalence, the solving code equivalence is at least as hard as solving GI, right? So maybe it's harder, we don't know. And then LIP is perhaps harder than solving any variant of CE. So I say perhaps because we don't know of any reverse reductions, right? If we did, then there'd be some notion of equivalence, but that's a really big open problem. So this is how the reductions work, but how well can we actually solve these, right? So I'll give you the best known algorithms. So for GI, it's quasi-polynomial time. So 2 to the log n. So n is the size of the input. For us, here it's the number of vertices, right? So this was shown by Babai. And then LIP is n to the on times s to the o1. So n is the dimension. So I should have noted this before, but a little bit different than codes. We can assume actually that these n by n matrices are full rank, right? So yeah, Euclidean space behaves differently than Hamming space, right, over FQ. So that's why we can do that here. Still gives us plenty of wiggle room. But here, when I say LIP runs an n to the on, n is that dimension, that rank. And then s is the size of the input. So some representation of these lattice bases, I'm going to call s, the size of that. So this was shown by Haviv and Regev. Okay, and lastly, LCE, because if we know how to solve LCE, we know how to solve the other ones. So using the best GI solver, this runs in 2 to the n plus little o of n plus q time, right? And then there's plenty more, but here, let me actually write. If I only care about deterministic solvers, so using no randomness whatsoever, this is the same, right? This is the time. But now if I'm allowing randomized sampling, right, I can do a little bit better, 2 to the n over 2 plus little o of n plus q. And then we also know of a quantum algorithm that runs in 2 to the n over 3, so slightly faster. Okay, and these were shown by, again, Bennett and Bias and others fairly recently, just this year. Okay, so these, all the best known algorithms we actually have for these are not great. They don't run in polynomial time, right? So yeah, it's still unknown like what the best one is, but so next time I'll actually talk about a little bit about the connection between like the understanding the hardness of these problems, of how to solve these problems, and basing cryptography on them, right? So some open problems that are out there is to show, like I mentioned, if it's possible to reduce LIP to any variant of C in any way. So there is a reduction, just one that I know of, for LIP to SPCE, but this uses an oracle call to the integer version of LIP. And it's only for a very specific family of lattices. Like they're literally built from codes. So it's like the equivalence is built into the reduction algorithm. But that's, yeah, that's one way. So this is a pretty tough ask to show that LIP reduces to any variant of CE. But we could also ask for a way to show that it's impossible, to show that there is some separation between these two kinds of problems, right? And then another one that I think has been looked into, but is definitely not known yet, is whether there exists a search to decision reduction for LIP, right? So can we prove something similar for LIP as we did for PCE and LCE, right? So this is unknown, right? Okay. Yeah, so this is all I had for today. about these problems. Yeah. Okay. Any questions?
The only little was in there.
Oh, sorry. Sure, you can go first.
The only little is up there are the SQ, the others are big ones, yeah?
Yes. Yeah. Pretty sure if I didn't write it wrong. Yeah. Question?
Alright, in practical life,
Mm-hmm.
what's the biggest field that is used for that?
That's a good question. We'll see that next time. Yeah, so there's a specific, okay, so maybe just a preview, but next time I'll talk about the Hawk crypto system, which is built on LIP, and they use specifically on module LIP. So if I'm not mistaken, they use, no, I don't know. I don't want to say something wrong. I'll check and show you next time. Yeah.
The follow-up question was going to be, does it affect the complexity of any of the lattice really?
I see. Yeah. Yes, it does. So yeah, I should have mentioned this before, but for the LIP problem that I stated, right, it's very general. But if you restrict like the lattices to certain like subfamilies of lattices, if you add additional structure, it's not clear what the hardness is. So there's quite a bit of work done on like attacking the families, like attacking these problems for certain specific families of lattices. So in particular, like this reduction that we had by Dukas and Gibbons, if I can find it. Yeah, this one for, no, sorry, not this one. No, sorry. Yeah, the reduction I mentioned from LIP to PC that uses, to SBC that uses that self-oracle call really to a specific kind of LIP over integers. Dukas and Gibbons show that too, but that's like for a very specific family lattice. So that's like an attack on this problem. Yeah, but I don't know about the other ones. That's open. No. Yeah.
You had a code equivalence example.
Mm-hmm.
More about that. You wrote SNs, I mean, direct delta.
This one?
Yeah, could you remind me what delta is?
Yeah, so I said it too quickly. So delta n is the matrix group of all diagonal matrices, right, with non-zero entries. Group of non-singular diagonal entries, diagonal matrices. Mm-hmm.
About randomized algorithm for LAP.
LIP, I don't think that's known. At least I don't know it, but yeah. Yeah. Any other questions? Okay. All right. So.